Hello, welcome to lecture 12 of EC 141. In this lecture, we will be talking about linear block codes. Note that this lecture will have three parts. Okay? And first, I will introduce to you block codes, how we use them, and what is its basic properties. In the next part, I will introduce to you some of the block codes that has been conceptualized over the past few decades of its existence, and finally how we apply block codes in detecting and correcting errors in our communication systems. Okay. So let's first examine your errors in communication system. Suppose we have a communication system with a probability of error that is 10 to the minus 3. So it seems pretty good. That's 1 bit error over 1,000 bits transmitted. Okay, but that's actually not good enough. Consider then a file mapped and converted into 250 symbols. And if there is 1 bit error, just one out of the 250 symbols, right? So 1 bit error, it's just a bit error. If there's 1 bit error, then you won't be able to reconstruct the file because the machine won't be able to understand it. So you can actually do this. You try to open a Word document in Notepad and then delete some chunk of data, and if you try to open it, the word processor would say that the file is corrupted. Okay, so if you transmit a file and then there's a bit error, then it could be a virus, it could be corrupted. Okay, and that's just a single bit error. And the probability when we try to transmit a file with 250 symbols having a probability of error, bit error, 10 to the minus 3, the probability of error or the file being wrong when transmitted is 25%. So 25% of the time, or one out of 4 transmissions of 250 symbols of the same file will always go wrong. Okay, and this is bad. You don't want your file to be there's 25% chance of your file being corrupted when you receive it. Okay, so how do you do this then? Well, maybe we could of course decrease the bit error rate. We want this to go down, maybe 10 to the minus 6, but as we know, we need to increase power. Okay? Increasing power to reduce the bit error rate, but increasing power that would be wasteful because power is actually limited, especially when you're trying to transmit in a wireless channel or even in a wired channel. If you try to transmit a high power, your lines, your wires could be overloaded and they could break easily. Okay, so let's look at the file level. Maybe there's something that we can do to, I don't know, detect the errors or correct them if you just don't want to detect them at all. Right. So let's first review how errors come about in our communication systems. So consider this discrete-time model of your additive white Gaussian noise for your channel capacity. Okay, so recall that for our model, a received signal is equal to your transmitted symbol plus your Gaussian noise with mean 0 and variance sigma squared. Okay, sigma squared represents the noise power, and the larger it is, so larger your sigma squared, the larger your noise power is. Okay, and we don't want that. Okay, anyway, so let's say we are working with some power constraint. You want your symbol to be transmitted. Its instantaneous power is less than or equal to some value p. We have to design a code, okay, such that we are only limited with this power right here. Okay, so before we go there, just recall your symbol mapping, maybe your 4PSK. Okay, so 4PSK, the constellation looks something like this. right? And if we distance them, if we make the distance between symbols large enough, then the received symbols, let's say this is xn, okay, then the received symbols are somewhere here in this circle, depending on the noise level. If the noise power is larger, then your y of n could be somewhere in a larger circle, which is centered on your symbols from your transmitter. Okay, you'll have a bit error if this circle right here becomes large enough that it has an overlap in its over the boundary that we will set depending on your decision rule. So let's say we're using maximum likelihood decision rule. Okay, so if we use that, then this circle crossing that boundary, as you can see, entails some form of bit errors. Okay, so this is what we call the sphere packing method, okay, to determine if we have errors. If we are constrained with a certain power, recall that the energy of a symbol is directly proportional to its distance from the origin squared. Okay, so if we're constrained with some power, then the circle that we will transmit is only dependent on its distance from the origin, and all the symbols can only be placed inside that circle. Okay, and when we add noise to that circle, or to the symbols rather, we create circles from them representing the distance that their symbol can be displaced rather from its original point. Okay, as you can see, so it's not quite clear here, so maybe there you go. We want our circles to be smaller, so we're able to pack more of them rather in our larger sphere. The larger sphere represents the maximum amount of power that we can transmit, and if we have more spheres inside the region, then we can say that our coding is more reliable than if we have less spheres inside this region. Okay? And there will be no error probabilities if you have no overlapping spheres right here. Okay, so that is the sphere packing interpretation of your coding. So how do we then reduce the circles, okay, and make our transmission more reliable? Okay, so basically what this slide says is that we can achieve the maximum capacity based on the sphere packing interpretation. Okay, so if we have 2 to the nr number of code words, that's the amount we can that's the amount of spheres we can pack inside the given your power constraint. Okay, that's the amount of code words that we have. This should be less than or equal to this ratio, which is the volume of the sphere, this large sphere, divided by the volume of the smaller sphere, which represents the symbol being transmitted, or the vicinity within the vicinity around the area of where your symbol is. Okay, so your highest data rate is given by this equation. It depends on the volume of the sphere you'll use. So how do we achieve it? So recall that this is equal to, here you go, if you simplify this, it's basically equal to your maximum channel capacity that is postulated by Shannon. Right. So how do we achieve this? One way to achieve it is to use the linear block codes. Okay. Property of a linear block code is that, let's say we have a word, okay, or a block of bits, or the message bits or data bits, with k bits. Okay, so we basically have k bits, and it can be written as a vector b with the bits arranged in this manner. Okay, so we will map these bits to a block of n. Okay, note that n is greater than k, and you have a coded bit, okay, coded word rather, or code word, which is also can be represented as a vector and arranged this way. So C0 here is the least significant bit, B0 here is the least significant bit. Okay, so all of this are bits, so they can either be 1 or 0. Okay. Your code is linear if we add two code words, and it will result into a code word from the same set of code words, set of valid code words. Okay, so as you can see, if you have k message bits, so you have 2 to the k possible messages, or 2 to the k possible symbols, whereas the number of possible coded bits you have is 2 to the n. But since we're only mapping one symbol from 2 to the k to the set of 2 to the n, there will be some values of 2 to the n, so some values or some combinations of 2 to the n that is unused, and that they will be invalid code words. So the valid code words would only come from mapping the message bits to an appropriate combination of n bits that form a code word. For example, we have a 5-2 code, so just note we're going to use this notation for the rest of the slides. When we have two numbers representing in a code, the first number will always be the number of code word bits, and the second number will always be the number of data bits. Okay, so a 5-2 code would mean n is equal to 5 and k is equal to 2. So from here, we have 2 to the 2 possible messages, and that is outlined here in the first column. You have 0, 0, 0, 1, 1, 0, and 1, 1, mapped to an appropriate code word with 5 bits right here. So you can see you only used 4 out of 32 possible code words. Okay, by doing that, you create distance from here, as you can see, from instead of having 4 large spheres, you have 32 spheres inside your bigger sphere. Okay, and only 4 of those, if you don't make them overlap, only 4 of those are valid in your only 4 of those are valid for your as a code word. Okay. If you did not receive a valid code word, maybe there's an error in the transmission. Alright, so the 2 bits here would be your data bits. The added 3 bits are called parity bits. Okay, so more definitions. So as we said, if we add two elements from your valid code words, it should result into a valid code word. If we add C1 and C2, so that's, oh yeah, and when we say we are adding code words, this is a modulo 2 addition from your definition of your definition of your finite fields. Okay, so if we add 0 plus 1, we have 1, 1 plus 0, 1, 1 plus 0, 1, 0 plus 1, 1, 1 plus 1, 0. So if you add C1 and C2, it will result into C3, making, well, if you try to add the others, some other combination, you will see that they will just end up within the set of your valid code words, which makes this 5-2 code, as an example, systematic. Sorry, rather linear. So a code is systematic if your k leftmost bits are the data bits. As you can see here, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. Okay, so that means this code is also systematic. Alright, So can proceed. Okay. So yeah, there you go. To make a systematic code, you have to use what we call a generator matrix. So pardon me, just ignore all the extra letters right here. Okay. There you go. So this is a generator matrix, which is a k by n matrix. Okay, and you multiply it to a row vector representing the message, which results into a row vector representing the code word. Okay, so these are just vectors that, and if you do matrix multiplication, you'll end up with your systematic code. Oh, sorry, not yet a systematic code, just a code. Okay, coding. Right, so that's just mapping your message to your code word. In your previous example, you have your 5.2 code has this generator matrix. So to verify that, let's take a code word, or a message word rather. Let's take 10. If we multiply 10 to the generator matrix, we should get C2. Okay, so 10 right here multiplied by the generator matrix. Okay, so the trick here, if you're multiplying your message to your generator matrix, you can see here that only the first column has a bit 1 and the other column has a bit 0. That means if you multiply this to the matrix, you're just getting the first row of the generator matrix. As you can see, the first row of the generator matrix is 1 0 0 1 1. Let's verify that. As you can see, it's not seen here. Let me just wait. Get that. There you go. Right, let's just clean up that clutter. Okay. Oh, there you go. See, 1 0 1 1. So that's what we got from here. The first row of your generator matrix actually corresponds to the code word 2. Okay, C2 right here, which came from the message B2. Alright. So to make a systematic code, your generator matrix should have the form right here. It should have an identity matrix and some P matrix. Okay, and it's called the generator for parity check bits. Okay. From your generator G, you can make your matrix H. We call it the parity check matrix. So the parity check matrix is, or has a form that's something like this. Okay. So if you transpose P and you have a we'll call this again your identity matrix, you get your parity check matrix. And the property of multiplying your parity check matrix to the transpose of your generator matrix, as you can see here, if you multiply them, so the generator matrix has this form, sorry, the parity check matrix has this form, multiplied to a generator matrix has this form, transposed. Okay, if you multiply this to an identity matrix, you get the same matrix. You multiply this to your identity matrix to P of P transpose right here, you get the same P transpose. And if you add them together, you'll get the 0 matrix. Right? So it doesn't matter that you add the same thing. Recall that 1 plus 1 is 0 in the Galois field 2 that we defined from the previous lecture. And 0 plus 0, of course, is 0. So it doesn't matter if you're adding the number to itself in the Galois field, you get 0. Okay. So what would happen then if we multiply code word by H transpose? So C, the code word times H transpose, and we know that the code word is equal to the message times the generator. And we've proven earlier that if we multiply the generator with your parity check matrix, you'll get 0. So this will be the 0 matrix. And you multiply the message to 0, you'll get 0. So a valid code word, when multiplied by your parity check matrix, results in a 0 vector. Any vector that is non-zero, Okay, any vector that is non-zero when multiplied to a parity check matrix tells us that there's an error. Okay. Tells us that there's an error in the transmission. So using this system, we can actually detect errors. And once errors have been detected, then maybe we can tell the transmitter to retransmit. Okay, that's one way of having a more reliable communication system. And this is only possible with digital communication systems. It's not possible with analog communication systems. Okay, so this is the summary of what we talked about, and I'll leave it to you to read. Okay, so we'll proceed. An example. So we have a 5-2 code. That's the same code that we had earlier. Your generator matrix G is this, and a code word is generated by this equation. Okay, so we want to list all the possible code words. So by multiplying, so let C be equal to this, your M is equal to this. So by multiplying this M with the generator matrix, you'll end up with this set of equations relating C1, C2, C3, C4, and C5 to M1 and M2. Okay. By doing so, I recall that all of this modulo 2 addition, or XOR addition, whatever you call it. So it results into this table right here. It results to this set of valid code words. So some notes: your zero vector is always present in a systematic code. So that is this vector. So if you have your message that is all zero, it should always result into an all zero vector. Any other combination of bits will make the code word invalid. So if we receive 11100, this is an invalid code word. Right. So I'll leave that as an exercise to you. If you multiply this with your parity check matrix transpose, you would get a non-zero column vector. Right. So if we can confirm, if we multiply the code words to your parity check matrix, you'll get the zero vector. This should be a vector. Right. This should be a vector. Right. So another example: determine the generator matrix given your following set of code words. So this is the mapping from your message to your code, and determine the generator matrix. Okay. So I suggest you ignore this next two slides. A better way to solve this is that you just take 0, 0, 0, 0, 1, 0, 1, 0, and 1, 0, 0. So I told you before that if you have your message multiplied to your generator matrix, if you take 0, 0, 1, then you're already, since 1 is at the rightmost position in the arrangement of bits, then you're getting the third row of your generator matrix. This one, second row of your generator matrix, and this one, the first row of your generator matrix. And it turns out that this generator matrix this is the first row, 1 0 0 1 1 0 1. Second row is this 0 1 0 1 1. Wait, 0 1 0 1 1 1 0. There you go. And the third row is right here, 0 0 1 1 0 1 1. So is the code systematic? If we split it here, you'll see an identity matrix and some parity check matrix. Yes, so the code is systematic. So if you there you go. So it's what we got earlier. Okay. So now let's define the concept of Hamming weight. So Hamming weight, or the weight of a code word. So C is an element of C, which is the set of all valid code words. Right. We denote the weight of the code word by this notation. Basically, it just means it's the number of non-zero components in the code word. So if we look at the 5-2 code we had earlier, then the weight of each element of your set of valid code words is 0, 3, 3, 4 respectively. Okay. And just some note, since for systematic codes there's always a 0 code word. Okay. For systematic codes there's always a 0 code word. Then the weight of that code word is 0, just one of all the codes, just the 0 code word, and nothing else follows. So now let's define the Hamming distance. So the distance between two codes, okay, so there's a concept of distance between them because remember, we're using the sphere packing interpretation, and by using more code words we can pack more in the sphere. Alright, so that creates the concept of distance between your two code words. Quite simply, we define the distance as the weight of their difference. And since we're operating in the Galois field 2, the difference between two code words is just their sum. Okay, so the distance between two code words is the weight of their sum, right? So if you have this, so if we take the difference between this and this, the weight would be 3. If we take the difference of this and this, the weight would also be 3. The distance of this and this, the weight is 4. The distance of the second one to the third one, so if we add them together, you'll get 1, 1, 1, 1, 0. The weight of that is 4, so their distance is 4. If you take the distance of this with this, that is 0, 1, 1, 0, 1, which is your second code word. Then the weight is equal to 3. And so on and so forth. So just to refresh your memory, when we have a distance between two symbols, we want to always maximize that. So you'll see later in a later part of this lecture that the greater your Hamming distance, the more reliable your code becomes. Okay? Right. So finally, your minimum distance and minimum weight are actually related together. Okay, so the minimum distance is basically if you take the set of all distances between any combination of two code words from your set, okay, take the minimum of that set, you'll get the minimum distance. That's what this equation says. And the quickest way to get that is just get the minimum Hamming weight, right, excluding the 0 code word. Of course, since there's always a 0 code word, okay, there's always a 0 code word in a set of systematic linear block codes. You exclude that because the weight of that is always 0. And we're talking about the distance. Okay, so talking about the distance, then there you go. As you can see, if you take the distance of all the codes from the 0 code word, okay, we'll end up with the minimum, okay, depending on the weight of each member of the code, right? So there you go. So for a set of valid code words, basically the minimum distance is equal to the minimum Hamming weight, excluding the 0 code word. So for example, so we have a 7-4 code defined by this generator matrix. So you need to be used to identify if your linear block code is systematic depending on your generator matrix. As you can see here, the structure of the generator matrix includes an identity matrix and some parity generator matrix. So we can say that this code is systematic. There you go. So with that, we can relate the elements of your code word C1 to C7 with the message bits M1 to M4. So defined by this equation right here. And we can generate your 7-4 code. So since your data bits is 4, that means you have 2 to the 4 possible message combinations, and that is outlined here. That's 16 of them, and each with their own code word And if you take the weight of the code word, so you see it right here, you'll see that the minimum Hamming distance is equal to 3. If you increase the minimum Hamming distance, again, you increase the reliability. Okay. So, yeah. And finally, to end this part of the lecture, what happens if you use block codes? Since we're using an extra n minus k bits for checking if there's an error in the communication, the effective data rate right here is equal to k over n times RB, where RB is the transmission rate. Or the amount of bits per second you actually transmit over your communication channel. Okay. So what this says is that our data rate, okay, is a fraction of the bits per second we transmit. So we're actually wasting n minus k bits per code since we are using them to check if there is an error in the transmission. Of course, if you have more parity check bits, as we call it, if we have more of these, we can expect a more reliable communication system. However, what that does is that we actually reduce the effective data rate for a constant transmission rate. Okay. So that kind of seems counterintuitive to what we want. So the goal of communication engineers is to approach the maximum Shannon capacity. Sorry, it's not 1/2, it's B times log base 2 of 1 plus SNR. So this is the goal of all communication engineers. But what if we want to reach this goal? I told you that we need to use coding. But if we use coding, we actually reduce the data rate rather. Like, take note, this is data rate. Like, it's data rate. So we can transmit at a faster rate than the data rate. There's nothing stopping us for transmitting the amount of bits over the maximum theoretical capacity. Okay? But what we cannot do is let the data rate that we transmit to be greater than your channel capacity. So this RB should not be greater than your maximum channel capacity. Okay, so that's the end of this lecture. If you have any questions, do not hesitate to leave a comment in the comment section below. Okay, thank you for listening. See you next.